I think that we will get started. So welcome everybody to, I believe this is the 17th webinar in our UG2 webinar series. And today we are focusing on industry in action. So thank you very much for all joining today. Just a brief agenda for today's webinar. I have some very exciting updates on behalf of UG2 to present, and then we'll move into our presentations. As I said, today we are looking at industry in action, so some case studies from a few of our industry partners. So thank you very much to our presenters for joining today. I'll finish with a wrap up, and there should be some time for some final questions as well. As always, I love to give a shout out to our UG2 steering committee that, particularly this year as we gear up for the workshop, are working very hard behind the scenes, helping pull everything together for that. So a huge shout out to them. They are helping us keep on track to meet the mission of UG2. And one of my biggest updates that I want to give today is we have relaunched the UG2 website. We still use the same URL, so underwatergliders.org, but it is all flashy and new. We have worked really hard to create a very visual, dynamic platform, which really will help us continue to meet that goal and that vision of UG2, which is to have a sharing platform where everyone can work together, share lessons learned, ask questions, and we can really promote partners and the work that everybody is doing. So I'm very proud of this, and thank you to everyone that was involved in helping with this relaunch. I wanted to share just a few of the sort of key features that we have on the new website. One, of course, is it's a great place for all of the resources that we have. So we have some best practices, some data management and tools. There's, of course, maps for current deployments. We have a publications section now. So if anyone has a presentation, a report, a publication of any kind that they would like to highlight and showcase and make available to UG2 community, please do so via the website. It's a really easy form now. You can fill out everything in a really straightforward way. And then that will be available to UG2 to access. We also, of course, have some history of sort of the origins of UG2 with some great photographs that sort of showcase the work that our users are doing. Of course, you can join UG2 directly and access all of the newsletters, the MailChimp letters, and the Slack channel via the website as well. So we sort of highlight some of the great features that you will have access to if you do join UG2, which is open to everyone and anyone as well. And then for me, one of the best features that I am continuously adding to now is our events calendar. So we have a really easy calendar now that you can access via the website to showcase all of the different events that are happening within UG2. So you can see there that the workshop and this webinar are now on there. I've also added some other webinars that are being hosted by the University of Washington. So with all of this, the biggest remark I have, I guess, is that this is for all of you. This is a platform, a tool for UG2 community users. So if you have anything that you would like to have added to the events calendar, to that publications, we have a jobs page as well. Please either you can do that yourself via the website, or you can always send me an email and I can update that onto the website as well. We really want this to be a highly used platform for UG2, which does mean we're relying on everyone to access this and to contribute as well. So please do check this out if you haven't already. It will definitely have a lot of use as we gear up to the workshop in September, which is my next major update. Most of you probably have received several emails now from us and some notifications on Slack. The UG2 workshop in September, registration and call for abstracts is now open. We're really, really excited. We have a great sort of draft agenda and some great sort of programmatic themes and ideas for this workshop. So please do, you can access the registration form either via the website or I've been sharing this also via Slack. And there's also a URL there that takes you directly to the workshop page on the website. The deadline is the end of June for registration. This is primarily for those that might require some travel assistance, sort of financial assistance to attend, as well as those groups that are willing or interested in helping with sponsorship for the workshop. So please do take a look at that. The call for abstracts is there as well as part of the registration form. There is no registration fee for the workshop. And we promised 3 really great days for everyone to come and share all of their work, as well as this being a really great networking opportunity and collaboration opportunity. If anyone has any questions about either the website or the workshop, please do send us an email. We are here to help, and you'll be seeing a lot more updates as we get closer to September. I also want to give a shout out to the International Underwater Glider Conference that is being held next month in Sweden. I believe registration for that is still open for a few more weeks. So if anyone is planning to attend, then make sure you register for that. That also looks to be a fantastic event and great opportunity to sort of network with more of that international group as well. And then finally, we always have lots of documents available for you to access. These also will all be available on that new website as well. So that's all the updates from me. 2 very big updates, but really exciting time for UG2. We'll move now into our presentations. As I mentioned today, we are looking at industry in action. A really core group or component of UG2 as a group is our sort of industry partners. They do a lot of really important work and strive very hard to meet the demands and the needs of very niche research questions and requests. And I believe they love a challenge. So we thought this would be a great time to really showcase the exciting case studies and the work that industry are doing to meet the goals that everyone else has. So we have some logos here to represent the sort of industry panel that we have for UG2. And we have 4 of those groups that were available today to present a case study. And our first is Shea Quinn. So if I stop sharing. And I'll let you share yours, Shea. Perfect. Great. So our first presenter is Shea Quinn, who's the product line manager of the Slocum glider at Teledyne Webb Research. He's responsible for driving the product line development for the gliders and bringing the voice of customers to the engineering and development process. Shea joined Teledyne Webb Research from Lockheed Martin, where he held several positions within the engineering group, including most recently engineering project manager. Over to you, Shea.
Thank you very much. Can everyone hear me all right? Great. Yeah, I'm very excited to present today. Thank you for having me here, and thank you for the opportunity to talk about some of the projects that we've worked on, particularly one project that I think I started to mention in the last webinar that we had, but really had some difficulties with my Wi-Fi then. So we're going to try to go into a bit more detail here, talking about the idea of being presented an interesting opportunity or a challenge by a customer and trying to work on a solution to that challenge. I couldn't think of a better example than a project that we did at the beginning of last year. We were approached to try to deploy a glider from a helicopter, which is something that had never been done before. And so I'll go into that today. So to give a little background on how this came about, the Slocum gliders are used as the glider for the LBSG program of NAVO, the United States Navy's oceanographic branch. They have a fleet of about 150 of these gliders, which are called the LBSG gliders, Littoral Battle Space Sensing Gliders. And these are deployed around the world. They have global requirements. About a third of that fleet is deployed continuously, but that can surge to 100 or more underway simultaneously. to meet the demands of the United States Navy in terms of the sensing that they're doing. Right now, these gliders are launched by TAGS ships, which are the research vessels of the United States Navy. They're large research vessels, and as a result, it does limit the global coverage of where these gliders can go a little bit. I think everyone here who's had to deal, with gliders being launched off of research vessels know that it's great to have the capabilities and the size of a research vessel, but in terms of getting places quickly or moving around, easily, you are a little bit encumbered by the vessel itself. So it's sometimes slow to reach high priority areas. The gliders have to return towards the ship for recovery. And for the mission of the Navy, there's often times that they've told us we need to get away from this model. And I sort of saw this. I know that the military deployments of gliders don't necessarily reflect the same missions that some of our, customers and other members of the UG2 community are doing with their gliders, but in a lot of ways they are. It mirrors the need of glider users looking for ways to deploy and recover more effectively, to be able to cover larger areas and do it in a way that's less expensive. And so if half of that problem can be solved, if at least the deployments can happen quickly and over a long, a far-reaching area, then you've at least cut part of your problem out and at least some of the need for these ships to go through there. So that sort of brought about this need for an air deployment. They said, if there's a way for us to more rapidly deploy gliders and get that data in a much more quick manner than sending a research vessel to the area of operation, then that solves half of our problem. In November of 2022, we were suddenly approached with the opportunity to perform a demonstration at IMX 23, which is the International Maritime Exercise. It takes place in the Persian Gulf, and it's led by CTF 52, which is a Commander Task Force 5-2. It was to be held in February and March of 2023. So if you're looking at that timeline, we were asked in November of 2022 to suddenly do a demonstration of this capability. And we said, okay, yes, we can do that. But of course, looking at that timeline, it's not a lot of time to come about with a solution that allows us to do that successfully. We were doing this also in cooperation with HM15, which is a Helicopter Mine Countermeasures Group. And essentially, the idea there was to demonstrate the ability to quickly deploy a glider from one of their MH-53E helicopters without a parachute or a cable from a 10-foot hover above the sea surface, what they call a 10 and 10, which is a 10-foot altitude and a 10-knot forward speed. It's the same situation that you'll sometimes see divers jumping out of the back of military helicopters from. So we said, that seems like something we can do. We've had solutions in the past for something similar. Deploying a glider in that manner is something that we think we can come up with a quick solution for and turn that around. This again was sort of meeting an operational need for a very specific mission, but we kind of saw that there's parallels between what they were doing here and stuff that could potentially be applied in the future to commercial or academic customers as well. So we just said, you know what, let's go for it. Let's try to make this happen. Of course, it came with quite a few challenges. The engineering effort itself was pretty steep. There's, first of all, just freeing engineering resources to work on the project. When you've got a planned timeline of which resources can work where, and suddenly that's interrupted by a brand new project that's dropped in, there's a lot of internal, freeing up of people that needs to happen. There's also just the technical challenges of dropping a glider out of an aircraft. It's something that is difficult to do, and especially to make sure that the glider stays in one piece and is, going to survive and be able to carry out its mission. The timeline was also a very difficult challenge. We'd had very little advance warning to demonstrate this capability. And also, in order to meet the timeline of when this demonstration was going to happen, we found out about this again, late 2020, November 2022, and we needed to have the glider and all other associated hardware for this shipped by early February 2023. So anyone knows anything about lead times of materials, and if you need to get something machined or if you need to get something ordered, there was essentially very little time to experiment, or a lot had to be expedited to make that happen. Another big challenge that we faced in this was a flight clearance. Anytime you're putting something into an aircraft, it has to go through a whole separate clearance process in order to get flight clearance, even more so than you would see on a ship or any other seagoing vessel. So there was a short timeline to gain this clearance. And it had its own requirements that went along with it. For example, there's no lithium batteries allowed in the back of one of these helicopters. There was also requirements for the engineering design effort that were suddenly introduced because of the flight clearance, in terms of how we had to strap something down, or vibration and shock protections, and how we had to make sure what would happen if to the glider if something went wrong with the helicopter, and vice versa. There was a lot of requirements that suddenly were thrown at us on top of the idea of designing something to drop a glider out of a helicopter. All the other safety features that had to be accommodated based on this flight clearance that we had to, design for, essentially. We also needed to physically fit check our solution with a helicopter prior to shipping everything. So again, this timeline just keeps getting shorter and shorter in terms of what we're trying to do. So we need to find a way to get our glider and our hardware in the back of one of these helicopters prior to this event. There's always some logistical concerns when it comes to customs and getting hardware, especially anything that's potentially related to a military thing in and out of a country. This particular operation was happening out of Bahrain, so working with the United States Navy and the government to make sure that this hardware got there in time. And then finally, the biggest part was the actual launch and flight. There were certain other restrictions that they had. We couldn't have iridium powered on while the glider was in the helicopter. And then the operational area that they wanted us to operate in had extremely shallow water, strong multi-directional currents. There were some keep out zones in terms of where we could and could not make sure the glider traveled. So it was a very challenging piloting operation as well once the glider got into the water. So looking at all these challenges kind of laid out in front of us, when we said, okay, I think we could do this, I remember bringing it to the team. And initially we said, I don't think we can do this, actually. We don't think we have the time or the capability to do this in a way that we think our glider would be successful in its operation. But then we kind of went back and we talked back and forth with our sponsors at the Navy a bit more. And we eventually realized we think we can do this. And we worked very closely with them and within our own engineering team here and our piloting team as well, and found a path forward. From an engineering perspective, there was quite a few choices that we had to make in order to make this happen. First of all, without lithium batteries, we had to have our glider powered by alkaline batteries, which is how our Slocum gliders were originally created, but it certainly limits the available energy for the mission. We had to create a glider launch rig and strap it to what is called a stub ramp, which is a shorter ramp that can be lowered at a sharper angle degree out of the back of the helicopter. We would then seat this glider in a specially designed launch cart that allows the glider to sit in there, similar to our the glider carts that come with each one of our gliders, by having a special ripcord that allows it to shoot out of there when you pull on that. Of course, accommodating all the vibration dampening requirements, tie-down straps in terms of flight safety, and then also knowing that because we were not allowed to be in the helicopter, and we certainly couldn't have any sort of dock server with us or any other control nearby for this thing, the glider had to be powered on with all its pre-flight checkouts complete prior to takeoff. We also had a, here's a little overview of what we actually brought with us there. So there's the LBSG style glider. We actually used one of our own gliders, but we outfitted it with a similar sensor package to the gliders that the Navy uses. We had our glider launch cart. You can see there, that's the specially modified cart that has the C-ring on a ripcord that allows that to drop. And then this launch rig, which is what would get strapped down to the back of the helicopter where the launch cart fits in and it gets locked in for deployment. We had to do some testing also about the launch itself. I'm going to play this video. That was a quick look at how that launch rig works, where you pull it and it slides forward. But we also needed to make sure that as the glider entered the water, that it would surface the right way. You're being dropped from a much higher elevation than we normally recommend for gliders to be dropped into the water. And as a result, we were nervous that if the glider was deployed in the same way we normally deploy our gliders, with the air bladder inflated and the pump pumped out the whole way, that it would enter the water not the right way, and that could potentially have a harmful effect on the glider. So we had to redesign the mission for how it was launched to allow for the air bladder to be deflated and the glider to enter the water more smoothly. And as you can kind of see here, after it entered the water, you'll see it pop up in this, beyond the boat that we did this testing in here in Woods Hole Harbor, all the way over there. So we essentially, not a great video here, but essentially you can see how we had to do some testing to make sure that the way that the glider was entering the water would allow it to smoothly dive into the water, go down, and then resurface about 20 seconds later. And that was the safest way for the glider to enter the water from that height. I mentioned also that we had to do a fit check. And when we talked to the people in charge of the flight clearance there, they said, well, yeah, you have to come to one of our bases and put it in the back of our helicopters. I said, great, where's the closest base? It was in Norfolk, Virginia. And from us up here in Falmouth, Massachusetts, that's about 11.5-hour drive. And because we were on such a short time frame, and I didn't want any problems with shipments getting lost or clearances getting in and out, me and another engineer just hopped into one of our company vans and drove the 11.5 hours one day all the way down to Virginia, spent the next day on the base doing the fit checks, and then drove the third day the 11.5 hours back. She's kind of hard to see because she's was wearing all black and is bad lighting here, but there's Fiona, our mechanical engineer, displaying our good work of actually fit checking this rig in the back of our display helicopter there, or demonstration helicopter there. And then this was kind of just an idea of what we were trying to accomplish, strapping this rig into the back of the helicopter, 10 to 12 feet above the water, and allowing that to be launched at that 10 and 10, as they said. Fast forward a month later, we've got the flight clearance. We are able to ship this to Bahrain. There I am in Bahrain. It took quite an effort to get it through customs, even though we thought we had set everything up ahead of time. But luckily, I was there for about a week, and we were able to get it through. You can see I was actually pretty happy to get it in the hangar there next to the helicopters, doing the first checkouts. And then the next morning, we had the actual flight launch. This was also a bit of a challenge in terms of the setup and pre-flight, what we had to do. I mentioned before, there's no iridium allowed on the helicopter itself. So when we did these pre-flight checkouts and make sure it worked, I did those on site using our FreeWave radio and a local dock server. But I also didn't have any access to the Wi-Fi because it was the US Navy's Wi-Fi, and I wasn't allowed to attach my computer to it. So we had to have my colleague, our glider support lead, Cordy Goodrich, awake at 2 a.m. on her computer halfway around the world, being the one to pilot this glider as soon as it hit the water. So after I did the pre-flight checkouts, I started the mission that would turn off the iridium, and I put it in the back of the helicopter. That special mission that we had to write was done in a way that as soon as the glider hit the water and went a certain depth underwater, about 3 meters, that would trigger the iridium turning on. So the iridium wouldn't turn on unless the glider reached a depth of 3 meters on the initial dive. So beyond just the idea of this glider has to survive its drop into the water, we also had to make sure it would dive to at least 3 meters in order to trigger the iridium to come on, so that Cordy, halfway around the world, could actually start piloting this thing. There's just a shot that I got as we were about to load it in. Here you can see these are some great shots. We did a good job of getting the GoPros in the back of the helicopter. But here we are loading up the glider, getting its wings on there. And then that picture on the far right there, that's literally me in the middle of saying, now I think this should work. And then we're on our way. Again, here's just some nice shots that the GoPro got of the event as it was getting ready to go. And again, some nice shots. Here you can see the crew in the back of the helicopter, preparing the glider for the drop, taking the pins out of that forward C ring. And then on the right there, you can see another shot captured by a chase boat that actually got the glider in air as it was falling into the water. You may notice, hey, that doesn't look like 10 feet. It wasn't. It was about 27 feet. And that was a lot higher than we had expected. So as I show you this video, you can see a lot of buildup. So you could see how the glider almost did a backflip because it was much higher than we had expected it to be when it got launched out of the helicopter. Luckily, it stayed vertical enough that it entered on its nose where we wanted it to. It dove into the water. It resurfaced 20 minutes later like we had practiced, and it had reached a depth of 5 or 6 meters at least where it turned on the iridium signal and was able to establish communications. So it all worked as planned, which we, each of those steps along the way, we thought there's a few different ways that each of these could go wrong, and luckily, none of it did. The one thing that made me nervous, meanwhile, I'm shoreside. I've just sent this glider off with no indication as to whether or not it's going to survive this drop. They were supposed to radio as soon as they dropped it and let us know if it survived. And we expected 20 or 30 minutes later to understand that. We didn't hear anything. And finally, at 40 minutes later, I decided to call Cordy, who's still up at 2 a.m., or probably closer to 3 a.m. at that point. And she says, oh, yeah, it's been in the water for about 15 minutes now. And they had just forgotten to call radio in and tell us that it had gotten in the water successfully. So that was a nice little mini heart attack for me. This is a quick look at the actual deployment itself. It was a very short deployment. It was just over 24 hours because that's the amount of time that they could dedicate resources to this. We had to stay within that rectangular box for various reasons. And so the biggest challenge here was that it was very shallow water. We were using a 1,000-meter glider pump because that's what we had available. And the water was 15 to 20 meters maximum. Additionally, because it's so shallow, it was very much affected by tidal currents. So you can kind of see, if you're familiar with our interface, these red lines represent the way where the glider's location was compared to where it expected it to be. So you can see how over the course of the 24 hours, it's getting pushed in many directions. But eventually, we got it on course. We were able to use our hybrid thruster option to move it in the right direction. And the next day, we went out on some rib boats that are sometimes operated unmanned and carry arrays behind them. But this time, we're manned operations, and we were able to go recover that boat. So it was a very exciting and stressful 24 hours, but we somehow were able to get this glider in the water, send it in the direction we needed it to, and recover it. in the Persian Gulf. So overall, a success story. I got to meet Commander Rojas, who is the leader, excuse me, Commodore Rojas, who is the leader of the CTF-52 and this IMEX event that later that day after we had done the recovery, there's another picture with the helicopter crew that actually dropped it in the water. And then also me with two of the officers that had the biggest impact on coordinating this and getting it done. So overall, it was one of those events where it was a tall ask. It took a lot of planning and engineering and coordination to face the challenges that we had. But ultimately, we were able to demonstrate a capability that hadn't been demonstrated before, work with some of our partners at the United States Navy to show how our gliders could be used in an area where they have not been used up to this point, and also get a pretty cool video out of it too. So that's it. Any questions?
Shea, this is Jeff Morrison.
Yes.
I'm curious, how strong were the tidal currents?
It was, I don't want to talk, it was strong. It was, I would say it's about, it was at least, I think like 3 to 5 knots in either direction, but it was constantly moving around, like constantly sort of shifting both ways. So there was times that it was pointed in the exact direction that we needed it to, so it actually helped us quite a bit. But then it was pushing us sideways mostly when we were really trying to get north to south.
So the tidal currents were basically normal to your path.
Yes, it was. Luckily, we weren't moving against them that often. It was more if they were pushing us side to side, kind of east to west, and we were heading north to south. So we had to adjust the mission to accommodate for that. But luckily, there were those moments every 12 hours or so that it was pushing us in the exact direction that we needed to go.
That's always nice.
Yeah.
Thank you.
Of course. Looks like Sean Beckwith.
Yeah. Hi, Shea. Thanks. I had a couple questions.
Sure.
Very interesting presentation. I just assume, Teledyne would have all the gliders available that you could possibly want. So you mentioned you didn't have much available to you. You had to use a 1,000-meter glider in a very shallow coastal area.
Mm-hmm.
Like curious why? Like, were you thinking, well, we know it'll kind of work, or was like that was it? Like that was absolutely your only option?
A little bit of both. We do have our own small fleet of gliders that we have with various pump options in terms of the depth that they're used for. But we also had some of those gliders already reserved for other testing or other missions that we were working on. So we also have operated our 1,000-meter gliders in shallow waters previously. I think we were a little taken by surprise by the strength of the tidal currents, and that kind of threw us off a little bit. But in terms of what we were doing, we knew that we could operate a 1,000-meter glider in 15 to 20 meters if necessary. It's certainly not the most efficient pump for operating in those depths, but we knew we could do it, especially with the idea that we knew this was also going to be a short mission. This was not going to be one where we would be deployed for a week or a month. We knew this was going to be a day or two.
Right.
So from that perspective, we said, we'll burn the efficiency on the pump. We'll burn the efficiency, or we'll burn a little more battery on the hybrid thruster, and that should get us where we need to get over the course of this very short mission on alkaline batteries.
Right on. And were those 2-hour surfacings, or what were you guys doing?
I think we started every hour just because we wanted to make sure it was, we had dropped so close to one of the keep out zone borders that we wanted to make sure that we were not heading in the right direction. And actually, if you look, we started sort of drifting in the wrong direction right away. But we got the glider turned around and then heading in the correct direction. So towards the end there, I think it was every I think it was every 2 or 3 hours we started looking at it, because again, we were really burning quite a lot of that alkaline battery with both the thruster and just fighting the current. So we were trying to conserve, and also the more time you spend at the surface there, we're getting pushed off target again. So we really wanted to limit the amount of surfacings that we had and just focus on staying underwater and moving in the right direction.
I did have an additional question. I don't think I missed it, but sorry if I'm asking something that I did. I was walking with my cell phone at first. Did you do anything to reinforce the hull? Because the first thing that comes into my mind when I heard about you guys dropping these things out of helicopters is, you know, they would buckle and something would leak through the O-ring, something like that. Is there any kind of additional support from section to section, module to module, or just kind of standard?
No, that's standard.
Okay.
We have so the launch rig that we used in the back of that helicopter was a modified version of something that we've used on some larger vessels in the past, where you can pull that ripcord and allow it to fall into the water. And that's something that, you know, we've seen work at, 3 to 5 meters potentially in the past off the side of a ship. So we've done that in the past, and as long as it hits it on the nose, the glider is pretty robust from that perspective. It's as soon as you start belly flopping the glider or having the glider land on its back, that's where the tie rod in the middle might flex. You get a crack in your sections of your hull and have a problem.
That makes sense.
So,
yeah, you're just compressing into the O-rings as opposed to buckling.
Right.
Awesome. Thank you.
Yep.
I think there's time for one more question, and I know Hank is eagerly waiting.
Hank.
Thanks, Georgia. Yeah, Shea, I think you mentioned this, but I missed it. Was this a G2 or G3?
This was a G3. This is a G3 glider.
Cool. And then I think it's a fascinating exercise in engineering. I'm wondering, what are the trickle-down effects from this experiment that other users who aren't using helicopters might benefit from?
You guys don't all have helicopters? No, I think what this was kind of able to demonstrate, there was a few things that we learned out of this that I think we've thought about how we can use what we learned from this to affect our greater customer group. One is just the rapid deployment using a similar ripcord system for gliders. If there are groups that are trying to deploy several gliders over a large area, potentially not stopping a large research vessel and allowing a glider to slide off the side or the back of a ship and go on your way is something that may be helpful. Also, even just, this is a small thing, but the way that we're able to deflate the air bladder and pump out the thing to get the glider to go into the water and continue away from a deployment vessel, that's something that we've started sharing with customers as well, in terms of a potential way, if you're, again, launching off of a ship that you're worried about the glider sort of going in and popping up next to the ship, potentially bumping the ship or the props or anything like that, having another way that the glider can enter the water and move farther away can do that as well. Outside of that, I mean, there's a few things that we learned from piloting in shallow water, piloting in high currents, and sort of demonstrating how a glider could potentially survive those situations. Yeah, there's a few smaller things like that. Like you said, not everyone here is using helicopters. Not everyone here is going to be having such crazy restrictions on the deployments and recoveries, but more than anything, it's the idea that we're focusing on ways to at least more creatively deploy gliders, so that again, if you're talking about the pain point of both deploying and recovering gliders often being the difficult or expensive part of glider operations, if we can ease any of either end of that, then it'll help the glider community as a whole.
All right, we'll have
Thank
to
you.
stop there, but there might be some time at the very end for any more questions. Thank you so much, Shea. I think that's a great example
Thank
of
you.
literally anything is possible. So our next presenter today is Laurent Beguery. Laurent obtained his engineering degree in mechanical design in 1998. During the first 15 years, his professional career began at the National Center for Scientific Research, where he first designed substation marine seismological measurements for the Institut de Physique du Globe de Paris. He quickly traveled the world to deploy these instruments to study seismic zones. He continued his journey with the National Institute of Sciences of the Universe and initiated the use of underwater gliders for oceanographic studies in France. In 2014, he joined Alseamar, where he continued to design and develop the use of the Sea Explorer underwater glider. Over to you, Laurent.
Thank you very much. Thank you very much, everybody. Well, in this presentation, the aim of the presentation was to explain what was the kind of mission, the kind of experiment that would make us the most proud and what some kind of success story. And this reminds me one of my earliest discussion with scientists back in 2014 when I joined Alseamar, where all the data, all the sensor you put on glider were not able to output real-time information. And that was very frustrating for the scientists. And they said to me, it's essential. It is absolutely essential that every sensor you put on a glider is able to give us at least some information in real time. And this has been a long journey that we have been following since 2014. And if we go to the next slide, I will talk to you about 4 different sensors. The first one we worked with is the AD2CP from Nortec, where after a few years, we managed to have a real-time current information and backscatter information from gliders. And I will show you on some missions. The second sensor I will show you is called the UVP6 from Hydroptic. It's a sensor for plankton picture and plankton size distribution. The third one is very famous, is a microturbulence sensor from Rockland Scientific. And then I will talk a little bit about acoustic. The aim of this talk is mainly to say, what kind of information can I have really in real time when I use those sensors? So the ADCP, if you look at what we implemented, the ADCP story lasted 5 years. We decided to implement the Nortec AD2CP because he has 4 beams, and 2 of them have a special angles that allows the glider, when it pitch down or up, to to still have 3 beams that are record very good data. And in order to get current in real time, we decided to use the VSBEC algorithm, and to get backscatter information in real time, we decided to use the Ellison algorithm, because there are 3 or 4 algorithms for backscatter, and we test them, and we decided to go for this one. For those who are not aware of what does ADCP raw data looks like, is the bottom right image. So it's more like noise to me than current profiles. So what we decided to do is that all the calculation, most of the calculation are done inside the glider, and some calculation that were required a better computer are done into Glimpse today. I will not go through the theoretical part of how to get ADCP current, because it's not the aim. I don't have enough time. And I will skip directly to some results on the next slide. So what you can see here is a picture of the Glimpse interface, which is our interface for piloting gliders. So I will use a lot this word Glimpse today in this presentation. And this is the last mission we did in a project where we wanted to quantify the quality of our real-time measurement of ADCP and delayed mode measurement of ADCP compared to bottom mode ADCP. On the right-hand side, you can see the process real-time ADCP, where the user is able to select how he programs the ADCP and what kind of quality control he wants to run in real time. And when you run the data, you obtain results like we have on the next slide. On the left part, what you can see is the direction of the current. So the experiment was a 5-day experiment, and you can see the tidal currents rotating from north to south mainly. And the picture on the right, what you can see is a profile of the intensity of the current in real time from the surface to more than 100 meters of depth. And this is distributed, in fact, on all our customers. So anybody using a Sea Explorer glider is able today to activate this module and to get this information in real time. But it's not the only information you can get from an ADCP. Another information you can get is a backscatter, which is the intensity of the return of the sound emitted by the glider. So if we go to the next slide is a mission that I'm very proud, because this is a mission maybe some of you had already been presented this mission. This mission is in the is offshore an island, a French island called Mayotte, in the Mozambique Channel. So it's very far from everything. And in this island, there is a volcano that is born in 2018. And very close to the island start to be release of liquid methane and liquid CO2 down to 1,300 meter depths. And the plumes, year after year, are getting higher in the water column. At the beginning, it was only 100 meter plumes. But as the year pass, now the plumes can achieve 300 meter below the surface. So there is a lot of gas that is emitted at this location. And all the little pink arrows you can see on the map are areas where you have plumes of liquid CO2 and CH4 that is emitted. Our job since 2.5 years is to stay in this area and monitor the anomaly of dissolved gas in the water column, but as well to monitor the plumes and the height of the plumes. And to do so, we are using the backscatter index of the ADCP. And what you can see on the right-hand side at the bottom, where it's a bright red picture color, is a plume, in fact, of those gases that are emitted 400 meters below that. So if we go to next slide, what you can see in real time in glimpse is, of course, a time series or profile of oxygen, CO2, CH4, and backscatter index. And in this example, I have added to you in gray what is a normal line. So you can see very easily close to the black arrows that the CO2 is weighed out of bound, that the CH4, which is not supposed to be present in the seawater, is very present in this during this year, and that the backscatter index that should be below 40 decibels rise more than 50 and eventually 80 decibel in between 900 meters and 1,000 meters. And if I draw the little picture you have at the bottom, in fact, you can see the glider doing its yaws between 900 meters and 1,000 meters, because we stay at depths. The color is the anomaly of CH4, and I put a little arrow to show the current, but you can guess it by looking at the yellow part of the CH4, and all the little bubbles you can see are the detections that are made from the ADCP. Of course, for our customers, this is not the product we show. We show the product that is in next slide. Every time we cross the area, we will send a report about the anomaly of dissolved gas. That is the top image in red and purple, where you can see the anomaly of CH4 and CO2 and the maximum you can see. The middle image, you can see the backscatter index. So you can see that it usually should be close to 40, but when we are close to a plume, it rises up to 80 decibels. The third image you can see in the center are the vertical velocity of the water seen by the ADCP in delay mode, in post-processing, because we don't do it in real time yet, where you can see that the water is really rising from the seafloor, and that really proves that we are on top of a plume of droplets of CO2 and CH4. And of course, you have all the bathymetric maps, and you have all the tidal, because tides have a very important effect on the release of gases in this region. So that is ADCP, of course, is a very important sensor. But today I wanted to show you another sensor that is important for us as well, which is called the UVP6, which is next slide. UVP6 is very similar. You have a sensor similar in US, the shadowgraph. It's very similar to the shadowgraph. It's taking images of a small thickness of the water in order to capture any particle, of course, but especially zooplanktons. And the first thing this computer will do, this sensor will do, is to be able to process the image internally and to give us information about particle size. So what is important when you integrate this kind of sensor as a manufacturer is to work very closely, of course, with the sensor manufacturer, because you need to exchange informations. And when there are big sensors like those one, we took a large consideration to make them fly as much as we can in order to improve the behavior of glider at sea. All the pictures that are taken are stored inside the sensor, but the sensor will provide the glider the particle size and particle density in real time, so we can have a hint about what we are measuring and where is the zooplankton. So if you go to the next slide, and because I'm sure you have all a lot of memory, you remember that this is the picture I showed you 2 minutes ago about the ADCP. So you can see the red part once again, close to the bottom between 900 meter and 1,000 meter are the bubbles detected by the ADCP. And if you go to the next slide, you will be able to see in comparison what the ADCP is looking out and what the UVP6 is looking out. And there is, in fact, a lot of similarities between those two pictures. We can see that they see the same pattern. So we are very happy about that. This mission was beginning of last month. So we are still working in the data set. But I'm very confident that we have a very good several picture of the bubbles that are underwater, because this is part of the thesis we are doing, is to better understand how the CO2 and the CH4 will dissolve as the plume is rising the water column. And if you go at the next slide, what you can see as well, and this is once again a direct view of the experiment through the Glimpse platform, you can see that we have several size of bubbles, and we can see those droplets at a different on the different class of the UVP6 in real time. So that is for the UVP6, what I wanted to show you today. And the next sensor, and hopefully if we go to the next slide, it's a sensor I would love to bring on the same time site of this volcano, is a microturbulence. And I know that in the US, a lot of scientists you are working with microturbulence. For this one, I would like to say that the integration for Alseamar was probably much easier because all the data analysis is done by Rockland Scientific inside the microturbulence sensor, and the good thing is that having real-time data for us, especially in this kind of sensor, is very good because we can check that the way we pilot gliders does not affect the quality of the data we produce in real time. So the good thing is that we now achieve a very good information in real time compared to delay mode, and that the sensor is very little affected by the platform, which is the glider. And I would like to thank Rockland Scientific, because they are a member of the UG group as well, for this very strong collaboration. If we go to the next slide, I have borrowed the results of Professor Donglai from VIMS, and this is one of his latest mission, where you can see that the dissipation rate we have in real time given by the glider is very close to the post-processed dissipation rate. The idea of having information in real time, once again, it's not all the time having all the information, it's having sufficient information to allow you to run your mission smoothly and to get the results you want out of your mission. So because this mission is not mine, I would advise you, if you can go to the next slide, to read the poster or any publication that comes out of this mission, because it was a very exciting mission to follow. And I think that VIMS and Alseamar, we are very proud of the results that were obtained during this mission. And if we go to the last sensor, which is on the next slide, where we had to build a complete payload, in fact. It's the only sensor that has been designed by Alseamar, because we couldn't find anything on the market able to do that or willing to do that. Is to be able to process acoustic data. So if you click once more, you pretend to go to the next slide, you will have this appearing. The idea is to bring an antenna of several hydrophones in order to be able to detect the direction of emission of sound, any sound, in real time, and to send information about that. So the first example of onboard algorithm we did, of course, is beamforming. And if we go to the next slide, please, and hopefully this will play automatically. It's a video. If it doesn't play, I would appreciate it if you can click on the button. No, the video. You have that? Okay, so sorry. So this image, on this image, what you can see is a couple of gliders which are flying mainly in the west direction. The blue glider, the green glider is C7, and the blue glider is C17. And the little red dot you can see on the map is our boat. And the two white arrows are the glider calculating the area from which the sound arrived. And if the video was playing, sorry about that, it would show that the glider are perfectly able to follow the track of the ship. And this is what we are doing when we want to do an acoustic barrier in order to detect any vehicle passing by. So if you go to the next slide. So what we decided to do on the glider is to equip the glider with a strong computer as a payload. This strong computer is able to work with artificial intelligence on acoustic acquisition, but is able as well to work on non-acoustic acquisition. It's meant to be programmed in Python or C++, and we installed inside the ROS, which is a robotic operating system environment for people who like to use it. And this allow any user to build their own algorithm and to detect whatever they want to detect. So for marine, for example, it would be sonar detection or things like that. And for people working with marine mammals, it will be more the specific species they are targeting. So this, in fact, allow you not to have acoustic data back on shore, but to have whatever results you want. For example, if you want to detect sperm whales, which was one of my projects, you can have real-time detection of sperm whales and real-time position of sperm whales if you are using several gliders. So that's what I wanted to talk about you as the most satisfying journey that Alseamar had with this glider. It's not on a single mission, but it's where we're able to take a sensor that can seem complicated at the beginning and bring it to be a real-time sensor in order to have the best mission possible. And if you go to the next slide, it's finished, and I have time for questions.
I had a
Anyone
question
have-
about some of the sensors.
Perfect. Yeah, we have time for one question. So yeah.
Unless there's oh, I see Eric has his hand up as well. Let's let him go first, and I'll ask mine later.
Thanks, Shea.
Hi, this is Eric Ream from Seabird. I was just curious, in the methane and CO2 detection, I wondered if you also had optical backscattering and how useful or not you found that.
So we do use optical backscatter as well, but when you're looking for a bubble in the water column, you will never find it with optical backscatter. This is why we had to move to acoustic backscatter. But when we were doing some studying on a resuspension process, actually the Ellison algorithm is pretty good to find consistent information with a backscatter of an optical sensor.
Great. We might have to move on now. I'm just aware of the time. There might be some room at the end for some questions. So our next presenter today is Greg Johnson. Greg Johnson runs RBR, the oceanographic instrumentation company with equally inconvenient access to all three Canadian oceans. With a background in electrical engineering and material science, he is keenly interested in building sensors that are not only extremely accurate, but also extremely easy to use. Over to you, Greg.
Thanks, Georgia. First of all, my apologies. My permission to give our case study fell through at the last moment from somebody who went, we want to publish actually, and blah, 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 blah. So what I instead rapidly assembled was really a much shorter thing, which is just a show and tell, both new things that might be of interest to both end users, but also to the Alseamars and Teledyne Webbs of the world in terms of revisions to our product lineup. So many of you are aware, and you just saw in Laurent's last photograph, a red brick, and this is the ABR Legato, as is this day. These days, it's rated to 1,000 meters, and obviously it's in a very awkwardly shaped package because it was the request that it fit into the hole where a previous sensor had already been put. And so that's why the cross section is rectangular. We recess it so that it's as streamlined as possible. The radius of curvature here is 220, which matches the Slocum, and we have other diameters for other manufacturers. And this is what we call internally the V1. And what I'm showing today is what is coming up, which is a V2. And by comparison, you can see that they fit in exactly the same hole, but the conductivity cell, although it has the same overall height, it's slightly bulkier. But if you compare the location of the thermistors, you'll see that it's much further forwards, and there are now dedicated guards around it, because instead of it being protected as it was by the nacelle of the inlet duct, so to speak, we brought it forwards to get into cleaner water and to have better thermal mass characteristics. We've also moved the pressure sensor to the rear of the instrument, and we've implemented 5 times better pressure sensor accuracy now, about 0.01%. What you don't see on the inside is that this instrument, which is available both in the dry bay version, this is the one where the electronics are exposed, and this is typically what Shea uses in the Slocums, or the wet bay version, which is what Alseamar folks or a number of other glider manufacturers use. Both of these now support additional sensors that can be wired through the CTD and have multiple rate sampling, so that up to this point, when that's been done, oxygen and chlorophyll and backscatter and what have you are all being sampled at the same rate as the CTD. A lot of people are taking advantage of the fact that the CTD can run at 16 hertz, but of course there's no point in measuring oxygen that fast, and the power consumption would be a waste of time given that the variability is so low. The new electronics permit a completely different scheduling for the sampling of the CTD versus any of the other sensors. So you could run something once every few seconds, once every 10 seconds, all completely internally. That capability will also be added to our deep water CTD for gliders. This is intended to sit in a wet bay where only the head or the body of the centaur sticks up. This is good to 6,000 meters for the deep glider work that is ongoing. It's also possible to attach additional sensors to MCBH connectors that come out of this end cap at the front. I think everybody's familiar with the Tridente, which is the 3-channel active optical sensor. Chlorophyll, CDOM, backscatter is the most common configurations. But what is relatively new is a version that's been optimized for going into the glider. So instead of needing the titanium back shell and the weight associated with that, and then the MCBH and the cost associated with that, instead, this is now intended to go into a dry bay mount. The curvature here matches that of the glider, and so it's completely flush mounted. There is a small orientation mark that you probably can't see on camera, but it's a little fiducial mark, which indicates which way should be up. So if the sensor is not going to be mounted vertically, but is able to be mounted on its side, then it is preferable to have the receivers pointing downwards because it gives you better sunlight suppression in near surface. And so that fiducial mark makes that clear. And the protocol and all the electronics and everything else is absolutely identical. So the OEM manufacturer of the float or the gifted user who is changing sensors over themselves is able to use all the same kind of proglets or programming interface as they have done before. And I think that is probably saving you a little bit of time, Georgia, because I think that's all I'm going to do for today. But really just to say, yeah, lots of, we appreciate the uptake of the variety of RED products across the glider world. And a lot of these second level developments have been driven by your requests. So please keep them coming. You can reach out to myself directly. You can reach out to our general inbox team. You can harass us at Ocean Science or the next UG2 workshop or in Sweden or whatever it's going to be. I think we'll have quite a number of us in Sweden, which is in about, what is it, months' time, 2 months' time, something like that. And then UG2, of course, in September, later on in the summer. Thank you very much.
Great, thank you, Greg. There's a couple of minutes if anyone has any questions for Greg.
Hey, Greg, I've got a quick question for you. At the UG2 meeting last year, you had shown me some preliminary sort of interface where the metadata for all the calibrations for all of your sensors is carried through the entire data handling process. And I thought that was extremely useful, saves us as end users a tremendous amount of time. I was wondering if you could touch on that and how that is going to work with both the CTD and the optics.
Yeah, Georgia, may I very briefly share my screen with the time I have available?
Yes, yeah.
Okay, so I'm just going to, there we go. And so you should be able to see my browser. And what I have done is just open a URL that anybody can poke into their browser. It's oem-lookup.rbr-global.com. And as the title suggests, this was instituted by us to support the manufacturing partners who are building vehicles, the Teledynes, the Alseamars, the Sea Glider manufacturer of choice, and the rest. This also supports our efforts in the Argo community. Traceability is really important to the Argo program. And so we have every instrument that we have built in the last 25 years is available with all of its metadata online. And what I'm going to show you and what you can do yourself is just simply take the example number that is visible in the form. So there's a serial number of an instrument. This one happens to be an Argo CTD, but the principle applies. And then there's an authorization key. And this authorization key at the moment is generated on a manufacturer basis. That is to say, Teledyne Webb has one that allows them to see the instruments that they have acquired. Alseamar has another. We don't have necessarily full awareness of end users, of course. And so we have not yet determined how best to make this available to you in particular, Hank, so that you could go and see the CTD that you have without it actually relying on us having correct ownership records. What we're probably going to do is just institute a kind of rate limiting step so that we don't get denial of service attacks and simply open them up so that you can put in any serial number and you can find them. But if somebody then tries to scrape the entire database of every instrument we've ever built, the website just automatically shuts you down after you've done more than X per day or something like that. But that's just a detail of this authorization key at the moment. The principle is still the same. So you can see down below here, we have, first of all, a line which is just composed, and it's a curl parameter. So if you were to run this from a Linux or Mac OS command line, you could use curl, and you put the same stuff into the parameter and say, basically, I'm looking for the serial number here. And then this is what it comes back with. It comes back with everything from the calibration coefficients that are in this logger for each channel at the moment. There's the temperature coefficient. There are the coefficients for producing salinity. Here is how pressure is corrected for various things. There are ways to look at other metadata as well. Let's just see which one of these is going to open for me. So this is some of the work that Eric has done along with Jean-Michel here to try and not only take a sensor metadata approach, but also up to a platform metadata approach. Again, this is driven by the Argo community saying they would like this, although I expect at some point it's going to become so easy for the people who are building floats to also offer this for gliders as well. But I can't speak on their behalf. I can just simply say that RVR is supporting this. And I think having full metadata all the way through the chain is useful. Let me just see. There is one of the JSON files which I was trying to actually get to open in my browser, but it just went to download it, which is not the desired effect. I can, on this page, click on Get Calibrations, and you see that I just got a zip file that opened. And in that zip file, I now have, come along, the PDFs of the calibrations that occurred at RBR, the data manufacturer. Actually, these are the latest calibrations that we're aware of. So we have a number of, an instrument might come back to us for a recalibration. And so when you say get calibrations, it's always the most recent ones. We also have a number of facilities around the world who calibrate to RBR accredited standards. And when they do that, those calibration certificates are stored also in our database, so that even if you were to calibrate, for instance, at Ifremer in France, you can pull up the latest calibration certificates generated by them there, and it will have basically a letterhead that says RBR and Ifremer across the top, and the technician signatures will be those of the people in France who did it, as opposed to anything else. That's one of the ways that we're kind of trying to encourage people to develop their own calibration facilities, follow a regular process that's routine and shared around the world. And we want to make those calibration processes completely public so that anybody can reproduce calibration if you've got the right equipment, but to still have a metadata form that allows people to be able to get those certs regardless of who physically happened to do that. So yeah, this OEM lookup tool is continually being improved with a number of different formats as that evolves. And this is probably the extension of what I showed you last year.
Great.
Yeah,
We
thank you.
will have to move on. Thank you so much, Greg, for that.
Thanks.
Okay, our final presenter today is Rob Ellison. Rob is the Director of Research and Development for Seabird Scientific. Prior to Seabird, Rob served as Vice President of Technology for Xylem's Analytics Division that included businesses such as YSI, Andorra, WTW, and Sontec. Rob has over 25 years of experience in developing innovative sensing solutions with a focus on in-situ sensing technologies for natural waters that enable higher resolution data to drive more informed decision-making.
Great.
Thank you.
Thanks, Georgia. And hello from a very sunny Seattle today. And thanks again to Georgia, Cassie, and the rest of the UCAR team for pulling this webinar together. I'm going to spend a few minutes doing a brief overview of our sensors designed for use on gliders and other autonomous platforms, and then provide a quick overview of an interesting case study by one of our customers. So I'll start with the CTD portfolio. We have 3 different products. The first 2 are pumped systems with options for integration, direct integration into wet or dry bays. So the most common one is what we call the GP-CTD, but both offer low profile external designs with various depth ranges. And we are able to directly interface our DO, our polographic DO sensor into the CTD package. The third system you see at the bottom is a package developed by APL at the University of Washington for sea gliders, and it integrates the same CT sensors that we use on our Argo floats into an unpumped, externally mounted system that they call the CT sail. So I want to speak a little bit about the benefits of pumped versus unpumped systems. As you probably know, accurate computation of the core physical parameters such as salinity and density requires knowledge of the temperature and conductivity sensor response times and the ability to temporally align their responses. Our pump CTDs guarantee that the same parcel of water is sampled by each sensor and a steady flow rate through the conductivity cell is desirable because the TC responses are known and can be matched. And the amplitude and lag period of the cell thermal mass error can be quantified and corrected in the data. Pumped CBER CTDs are also outfitted with our very effective anti-fouling system. So for particularly long deployments or deployments in very productive waters, that can be very critical. Here's a field example that highlights the impact of having constant flow through the CT duct. In this case, we mounted 3 CTDs to a profiling frame with an SB9+, sort of our premier vertical profiling system as a reference, and then 2 GP CTDs with different sampling regimes that were lowered through the water column at around 50 centimeters a second. Excuse me. The TC data from the 9+, which samples at 24 hertz, were temporarily aligned and thermal mass corrected to produce an accurate reference profile for comparison with the 2 glider CTDs. The glider CTDs are in the red dots and the blue dots. The red dots is a CTD that was configured to pump continuously during the profile, and the ducted TC sensors at a constant sampling rate, the pump rate was a constant 10 milliliters per second, and this CTD was sampling at half a hertz for every 2 seconds. The blue dots is a GP CTD that was programmed to run the pump for 2 seconds, and during which they would make a measurement, then turn off the pump until the next sample at a rate of sampling every 8 seconds. The figure on the left shows the uncorrected GPCTD data with clear errors compared to the reference, particularly in those 2 zones in the orange boxes with rapid salinity change. The figure on the right shows the GPCTD data, both of them with the dynamic corrections applied for the TC temporal alignment and the cell thermal mass correction. And you can see that the error is significantly reduced compared to the far right. From the left graph. And then these corrections are possible because of that fixed flow rate past the sensors and the fixed sample rate of both CTDs. Once aligned and the cell thermal mass corrected, the salinity profile from the continuously pumped CTD that's sampling every 2 seconds agrees very closely with the 9+ reference. Despite the same corrections applied, the improvements to the blue dots GPCTD that's sampling every 8 seconds and periodic flow going on and off is clearly less successful given the slower sampling rate and the discontinuous pumping. So with that, I want to move on to some of our BGC sensors, biogeochemical sensors that are typically mounted separately to the CTD. And often these need access to the environment, optical measurements like chlorophyll and radiometry, and are mounted so that's facing either up or down in the water column. The EcoPuck is the first one, and it's probably the most common sensor that's used. And similar to what Greg said with their product, the most common configuration is chlorophyll fluorescence, backscatter, and CDOM. We do have the COL, which is that picture, the titanium housing on the right, which is an oil and water and backscatter sensor. We have a variety of radiometers, 4, 7, and hyperspectral radiometers that can be integrated. The most common is the 4-channel. We call it the OCR 504. We also have our UV spectrometer, the Suna V2 that measures nitrate, and both polographic and optical oxygen sensors. And we have been working with some researchers over the past few years in the development of a ISFET-based pH sensor, specifically designed for autonomous platforms. A lot of exciting developments there, but it's not a release product yet, but we're working hard on that. So really quick, I want to highlight one of our customers, an interesting case study from one of our customers. This is from a paper by Christian Rees and his team at the Antarctic Ecosystem Research Division at NOAA's Southwest Fisheries Science Center in La Jolla. The goal was to test the accuracy of a glider outfitted with a unique sensor payload to estimate krill density in the Antarctic, working towards a system that can ultimately either supplement or replace annual survey cruises in this extremely remote and dangerous part of our oceans. Research to further autonomous platforms capabilities such as this will lead us towards operationalization of gliders. That is an extremely exciting prospect. And that will lead to higher resolution data that is safer and less expensive to collect. The team here used 2 Slocum G3s outfitted with our GPCTD eco triplets, an Ondura optode, and ASL Environmental's 3-frequency acoustic zooplankton and fish profiler used to estimate the krill biomass. The comparisons were done between cruises that were going on simultaneously in the same area at the same time as the glider surveys, and with some really promising results. There's still a lot of work to do. They're not perfectly matched yet, and there's a lot of tweaking to do with the sensor settings, with the deployment processes, but it's just a sign of exciting developments of getting to a point where we can really operationalize these like for fisheries that have been done for other applications already. So with that, I'm going to wrap things up. I want you to know that we are actively working on next generation sensors for autonomous platforms, and would love to invite any of you interested in sharing your ideas for improvements to sensor payloads to reach out to us, whether it relates to the integration, development of new sensors, the maintenance, the software. We're interested. So please reach out to me directly, and I would love to set up a time to schedule a discussion.
Great. Thank you so much, Rob.
Sure.
If anyone has any questions, we can probably do one question. I will be sharing just a few links just in the chat for the registration form. And my final remark is, well, 2. 1, I think any of these industry presenters and groups love to hear from everybody with questions, comments, requests, hopes, dreams. So please do reach out to them. And then if anyone else belongs to an industry organization and wants to join the UG2 industry panel or have logos on the website, please also do email me. We are happy to have anyone else on board for that as well. So are there any questions or a question for Rob? Great. If not, we will end it here. I just want to thank our 4 presenters again for your time and everything that you're doing to help sort of push the future of gliders into fruition. I really appreciate your time today, especially. And I believe all of these groups will be present at the UG2 workshop in September as well. So another great opportunity to meet with them and again, have those conversations and write the wish list. So thank you all so much. Please do register for the workshop and check out the new website as well. And we will see you again in July. Thank you.
Thanks, Georgia.
Thanks.